The words cycle, bike, and bicycle are all closely related. But how does a computer know? Humans are very good in recognizing a face, but for computers, such recognition is typically hard. The reason behind this is that the computer programming language of computers is built up in a very logical manner. And this is not quite compatible with many of these problems. So instead of this standard programming language, we can also take a different approach, called machine learning. Machine learning algorithms are more flexible when it comes to dealing with situations that are slightly different every time, or when the data is noisy. They're also really good at inferring patterns from large data sets. This makes them very useful for applications such as self-driving cars or face recognition. So, machine learning is the discipline of learning patterns from large amounts of data. Instead of coding complicated algorithms into computer programs, the idea of machine learning is to show a simple computer algorithm lots and lots of examples of correct and wrong behavior. For example, if we want to train a computer to recognize a cat, we could show the computer many examples of cats. This is a cat, this is a cat, this is a cat. Hey, this is not a cat. In this way, the computer starts to learn from the data what the expected behavior is. The requirements for these kinds of algorithms are enormous computing power and the ability to work with many data points, thousands, millions, or even billions of data points. This requirement of scale means that machine learning techniques, even though they have been known for decades, have not been used in real-world situations until very recently.
How can quantum solve this?
As machine learning is a vision or an approach rather than a single algorithm, it is not immediately clear what use quantum computing code could have for machine learning. However, upon closer inspection, it becomes apparent that many machine learning techniques rely on more basic tasks, such as linear system solving for their functioning. Linear equations can be efficiently solved using the HSL algorithm, named after its inventors Harrow, Hessedum, and Lloyd. However, as we will discuss in a moment, there are significant challenges in the realizations of this approach. Another cornerstone machine learning technique, called principal component analysis, can also be speeded up significantly on a quantum computer. Principal component analysis can be understood as identifying the most important parts of a large matrix and using these to describe the matrix. If we return to our example of recognizing cats, we could show a computer many examples of cats and use these images to create an average cat. To reconstruct individual pictures, we start by using the most important variable, which is the one that gives the largest variance. This could be, for example, the size of the cat, but it could also be a combination of factors, for example, a combination of weight and size. It could also be something else. But the computer will find out by comparing all images. The variable with the largest variance is the first principal component. After that, we can just take the second most important variable, the third, and so on. In doing so, we end up with a set of equations that can reconstruct a cat to desired accuracy. While this is a powerful way for recognition, it is still hard for classical computers. The quantum algorithm for principal component analysis is called the LMR algorithm, named after Lloyd, Moiseni, and Raymond Rost. This algorithm can provide an exponential speed-up and would therefore be highly valuable.
What are the caveats?
Because the advantages of quantum machine learning mostly rely on the HSL algorithm that can be used to solve linear equations, all caveats related to solving linear systems apply here as well. Perhaps the most significant challenge is the data input problem. This is especially challenging for machine learning algorithms, since by design we're dealing with very noisy and difficult to parse data. This means that finding an efficient way of storing this data in a quantum memory, or QRAM, for later reference is highly non-trivial. A similar encoding problem holds for the LMR algorithm, used for quantum principal component analysis. If we can overcome these challenges, there will be many applications for quantum machine learning. Application areas can range from security, for fast recognition of persons in large crowds, personal advertisements, medical applications such as recognizing diseases, or even for accurate prediction of the weather.